Today I'll be discussing on the chapter 2, our subject on the discrete time signal and system. This will be this will be part 1 for the chapter 2. So I hope that we will focus on the what we call it discrete time signal for today. So yes, everyone here right now. Okay, now me and 17 attendees. So yes, okay. So the first of all, I would like to introduce the outline for today. So basically, for today we'll be covering the 3 subchapter, which is related to the some introduction of discrete time signal representation. Secondly, will be elementary discrete time signal, what is all about the discrete time and the signal itself. So the thirdly will be the discrete time system, which more or less on our target for this one. So then for the fourth and the fifth one will be covered maybe next week, I guess, because if we have time for today. So before I begin, basically I would like to show you something about there are things can be considered important in our signal system. So yes, okay, first of all is discrete time signal representation. So how is the signal is represented? Signal is represented. Basically, we have several representation. So normal way to represent the signal would be the functional representation, which we will use the xn, the conditional value 1, 6, 0 for n 1 and 3, n 0 and 7, and elsewhere. So and then we have this is what we call it. Normally we call it input. So for y, we will call it as the output. So yeah, from now on we call it this input and this output. So this is the output will be 0 for less than 0, 0 for 0, and the rest from 1 to 102 will be n power of n, 6 power of n, sorry. And then the n larger than 102 will be 1. So this will be the conditional for the output. So this is the idea whereby the functional representation is all about. So the secondly, we have the graphical representation. So the graphical, basically this, I guess, many of you knows about this graph, right? So how to build it. So what is the suggestion? What is the software that we can use to build this graph? Any suggestion from you guys? Okay, this one is MATLAB, obviously. So this one, okay, before I begin, let me clarify the things first. When last week, we did discuss about the X and sorry. Last week, what we did is we discussed more on if you can remember this, right? Okay, so and then this. Okay, so yes, I erased this one. So basically, when we talk about xt and xn, so in this particular issues or subject, we will tell that the t is the continuous and the n is discrete. Right? We did discuss it last week, right? So, but in this slide, basically, this is because we actually sharing the slide between our colleagues in FTKK. So basically, this for this case is not a good example over here, but the original one it should be like this, because the n itself and this sharp bracket is referred to discrete, not the one that we have like this. Okay, So when we talk about the straight line, then it refers to the continuous. But if we refer to the the bubble and the dot over here, then we call it as a discrete over here, discrete time signal representation. So that from by today, so basically I would like to pay your attention and try to use this as this one as discrete. Okay, so be careful. So meaning this one also sharp bracket. Okay, right. So the third way to represent the signal is we can tabulate it as a table, like 2 times 7 over here. We have n. The first row would be the integer of the number. So we have minus something from the minus infinite, let's say, until 2. So then this is xn. So here also we need to remember that this is sharp. So this is the value of the n. So meaning to say, if we want to build up the graph, this is n, this is xn. So, and this minus 2 over here, right? There would be this one, could be this one, would be this, and this one could be that, 5, and this one could be this. So this is the way, because this is actually graphical, but the way that we discuss now is actually the tabular representation. So while the fourth one is a sequence representation, whereby the xn again will be using several sequence number in such bracket. Okay. So we know that the signal is represented by several numbers, several numbers over here. Okay. So before I start to jump in, what's this? Okay, okay, okay. So before that, let me introduce one thing about. Any one of you heard about this theorem before? Anyone? What does the Nike set is the Fs is actually needed to be as 2F max. Okay, so meaning let's say we have this sine. So the sine, the frequency for this, or we say that 10 hertz. So what is the lowest frequency sampling for this signal? So say that this is F max.
20.
So meaning this Fs should be 20 or more, right? So this is the way that we discuss in the signal. If you cannot give the frequency sampling as at least 20, so let's say you have 18 or 15 or something. So basically, we will face things that regarding to the. Have you heard about this?
Yes.
Aliasing. So it depends on the how we pronounce it. Okay. So for making things clear, aliasing. Hold on. What should I do for this time? Can you see my screen right now? The blank screen? Can you see?
Not yet.
Okay, not, okay. Sorry. I share you again. Okay.
Yes.
So basically, this is actually a terminal in Ubuntu to say that where am I now? So this is this, okay. So basically, I just want to show you the Python code. This is the Python code basically for sampling. So, oh my god. this is, can you see well or it's difficult? So this is a, okay. This is a Python 3 coding for describing the sampling Nyquist theorem. Would be the sampling bandwidth for the, let's say, 40 hertz that we have fx over here, f40 over here, and this will be the link space. It's actually the things regards to the how we show the sample, and this is the plotting one. So the plotting for the signal, and this is actually plotting for the NT. So NT is stand for T equal NT. So meaning this is actually the sampling, the length between one sample to another sample, the point to sample the time in T to N. Okay, so this is actually when we put 90 hertz for the case based on 40 right here. So this one is just nice, like somebody said, when I give 10, that means 20, right, just now? So if I give 40, meaning the less is 80, right? Okay. So then this is 75, meaning lower than the less one. Okay. So these are the codes. So basically, if I okay, I can see that this is the one that I want to show you. Basically, how to show. It's difficult. Hold on. Okay, one idea. Okay. I stop it first. I change my mind again. So everyone has Gmail, right? Hope.
Yes.
Hopefully.
Yes.
Okay. Everyone got D drive, right? Drive.
Yeah.
Okay. So can
Yes.
basically if I put here, so I just now I'm using the Google Collabs. If you guys know about this, it's similar to the Python just now, but this I just borrow from the Google per se. So this is actually some codes that I run for. This is not good for explaining, but let me connect this first. Okay. So this is actually want to connect. Okay, fine. Connected to the Google. So now what I have is a 12 gigabyte of RAM and 100 gigabyte of storage PC for free. Okay, so now the things is similar. So I put here because this is more brighter than just now. Okay, so the thing is, if we run this code, the similar as the one that I run in the terminal just now, this, okay. If I put it this way, okay, now we can see that we have, okay, say that this is actually, this is a figure size. So this one is separating two figures. So the two figures, the first from 2 and the second from the 2. Okay, so this is for the first figure, while this one is for the second figure. So hopefully you can follow me. So the one that I said just now is by default in my slide just now I put it 10, right, hertz, and somebody said 20 at least, right? Okay, so for this case it's 40 hertz. Okay, so when we put 80 hertz as the sampling, and this is 90 hertz, and this will be the result. The blue is 80 and this is 90. Can you get the idea? Okay.
S.
Now, the right side of the figure will be this one, 1, 2, 2. So meaning the second, the second from the 2. So meaning the right hand side. Okay. Similar, we set it for T as the frequency, and this one is 80. 80 is actually this dot 40 is this line, blue. Okay, so then, so for this case, I try to set 75, which means less than 80, right? Can you get me?
Yes.
Okay, so now, can you see that the red line is actually crossing the original blue line? Compared to this one is actually one by one, satu persatu dia punya sampling dalam skop biru. Nampak tak? Tapi while here, kalau you tengok kat sini, yang ni dia ambil daripada yang sebelah, the left neighbor. But suppose this time to be here. And sudden, this is actually the sebelah one, and this will be the sebelah lagi. So maksudnya, yang ni we call it alias. Dia bertindih tau. Dia rampas signal lain. So that will be what we call it aliasing effect. So meaning to say the most easiest is here. You can say this 1, 2, 3, right? And
Yes.
this one is 2. So meaning 3 and 2 will be collapsed. So let's say I put it 45. And things will be worse, I guess. This one will be easy to you see. So instead of we have how many pulse, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 22, we have only 3. You rasa berbaloi tak nak sample 3 ni daripada 22? Tepat tak signal ni? Tak kan? So that's the reason why Nikes came across that this should be 2 max at least. So that's the reason why the 41 need to be multiplied by 2 for sampling. So we need to sample by 80s, not less than that. So otherwise the aliasing effect will be occur. So that's the way it is happen in the signal field. So meaning this is actually very well known. This one, Nike's theorem. So every single people dealing with signal, so just a code. Okay, now I think that will be okay for that. So now we will jump to the elementary discrete time signal. So for this time, I will show you guys the how we represent example here. The first on the top is actually unit sample. So unit sample would be the things related to, if you're familiar with. And this one, unit step, is by default is this. And this one too could be UN. And this one is different way. Okay. So unit sample meaning from the, what is the name for this function? Can somebody tell me the name of this function?
Delta function.
Some say delta function, impulse, chronicle. So that it depends on how we interpret. So basically in signal, normally we call unit sample as delta function. Okay, nice. So then, okay, now coming to the ideas of d delta just now, this delta. So by here we also need to change this, right? And this one, okay, this one, right? Okay, 1 is actually the 1 is only happen at 0 and the rest will be 0. So meaning hanya satu je tempat ada nilai di n. Okay. So the shifting properties is basically carries into the time, discrete time. So basically this theory is coming from this. So this is actually the original things, and it is actually similar to the one, sorry, not here, here. Okay. So when we talk about the continuous time signal, basically we deal with the integral, right? So meaning every single things happen in this line is considered as delta tau. Okay, so the summation of delta tau is actually known as integral. However, in the discrete time signal, so whereby the most well-known and the most well-used in discrete time signal is unit impulse, unit sample. So meaning we call it impulse later on. So because anyhow, anything regarding to the t is actually converted to the n later on. So in order to reflect the idea of discrete, so basically this t will jump into every each. So meaning this is delta 1, this is delta 2, delta 3, delta 4, delta 5, so on. Okay, so then what we have in the continuous 2, we have delta n, what can we call it? This is n. So this n is actually refer to where's the location that the impulse happen. Say that we have delta n minus 1. So where is actually location of delta minus 1? So it will be here, right? Because n minus 1 equals 0, n is 1. So that would be here. So it reflects the where does the n is selected by just a specific application.
Okay, thank you guys for watching NMZH channel. Hopefully you can get knowledge and benefit from the videos. Thank you so much. Assalamualaikum.